Oh, we got a huge turnout today. Okay. We're going to finish up talking about the Sudoku solver today. So finish up that recursion, and then we're going to start into trees, which is going to be consuming us for the remaining 3 weeks of the course. Before I get started, there was just an interesting newspaper article I read the other day, which if I can remember, I'll dig it out and um, distribute to you. So it's an interesting article about note taking. And they did a big experiment to see whether it was better to take notes by hand or by laptop. And they had some interesting discoveries. So the overall finding was that you retain more information when you take notes by hand. Now, they're more nuanced than that. So if you take notes by hand, they found on average, and remember, this is huge number of people, so you may be more or less, but on average, people who write their notes write about 22 words a minute, and people who do it using a laptop write about 33 words a minute. So people who take notes with a laptop, in fact, do take about 50% more notes. And when they're tested, students are tested right after class using quizzes. The students who have taken notes using the laptops do slightly better than the students who have taken notes using handwritten notes. But when the students are retested a week later, the students who took handwritten notes performed significantly better than students who took notes via laptop. And they hypothesized the reason is that when you're taking notes by hand, it forces you to think more about the material and to mentally organize it. Whereas when you're doing it with a laptop, you can pretty much keep up with what I'm saying, and so you kind of are more superficial with it. You just can kind of type it in without really having to think about it. And so your knowledge or remembering of the material is more superficial. Not saying you should not take notes by laptop, but I found that it was interesting. It is, having done it both ways, it is significantly harder to take them using handwritten notes because you are slower and you don't get as much. And you end up summarizing what the instructor says. So at any rate, I found it was an interesting article. And like I said, if I remember, I know I threw it out. So I have to dig it back up, and I'll hand it out if I can find it. Okay, so that's the little vignette for today. Any questions from last time about recursion? Okay, so like I said, we're going to finish up, and if you remember, what's recursion really good at in the context of puzzle solving? Both Towers of Hanoi and Sudoku, what's its strength? Backtracking. So being able to roll back a solution to a previous state and trying again. So with the Sudoku problem, what we were doing was we were filling in the squares starting from the upper leftmost corner, and we were doing a brute force search where we would start with 1, then 2, then 3, and as long as the number satisfied the 3 conditions, unique in the row, unique in the column, and unique in the panel, then we would move on to the next square recursively. And if that worked, we returned true. If it failed, we rolled back and picked up with the number with the next number. So if you remember the solution, get the solver. Initially, we just start by calling recursive solve with 0, 0. That's the first square. Then what we do is move forward until we find a dash, because that will be a square we have to fill in. And we keep incrementing the column. If the column becomes equal to 9 at the edge, we increment the row. If the row becomes equal to 9, we're done. That's the base case. and we return. So remember, every recursion has a base case that terminates the recursion. In the case of Sudoku, it's the case where the puzzle is completely solved correctly. So once we find, so this loop right here is just trying to find the first empty square. And then for each item from 1 to 9, we set that particular square to be equal to I. Then we check our 3 conditions. Is the row valid? Is the column valid? And is the panel valid? And if it is, then we call the recursive solver. And remember last time we could have said R comma C plus 1, except C plus 1 might be past the end of the puzzle. So we simply leave it to the recursion to find the next empty square. And if the numbers work and it's able to solve the rest of the puzzle using that number, we return 1. If it fails to solve the puzzle or any of the 3 conditions are violated, we simply move on to the next number. Okay? And then at the very end, if we drop out of that for loop, it means that none of our 9 numbers worked. So that means we backtrack, and the way we backtrack is we reset the square to be empty by setting it to a dash, and we return 0. Now, if you also remember, this was our data structure that we use. So print screen prints a nice image of the puzzle to the screen. Print convert prints a nice bitmap image by producing input to a really neat program called convert that is able to convert images from one format to another. In fact, it's worth showing you. So if on a Macs, does anyone know what Macs produce their screen grabs in? Something called TIFF format. So if I, on my Mac, go to Finder. Whoops. You can go down to Utilities, and there's a program called Grab. And that allows you to grab a screen shot. So let's do that. Capture, in this case, I'll capture a window. So this is the window I want to capture. Well, it didn't like that. Let's do it again. Did I catch it? Oh, I did. Here it is. This is the screen grab right here. Okay, so this is what I did. Unfortunately, it's in TIFF format. So if I save it, I'll save it into my temp directory. So I'll call it BVZ. And save it into my temp directory. And if we go into my temp directory, we see that it was, wait, that's not good. Where did it save it as bvz.dat? Save. Huh. Let's do that again. Capture, let's do selection this time. Save it. BVZ. Replace. Ah, that's why. Go into temp. It's saved as a TIFF file. Unfortunately, the only browser in the world that recognizes a .tiff file is Safari. Try to put that into Firefox and it won't show up. Firefox likes JPEGs. That's a problem. So I want to convert TIFF to JPEG. The way to do that, I don't have the convert program on my machine, but it's on the Hydra machines. So I go and dump it onto the Hydras. And I log into the Hydras. And then on Hydra, there's a handy-dandy program that is called convert. And it converts pretty much any image to another one. So if I say convert it from TIFF to JPG, knows what to do. Now I have a nice JPG file that I could display in Firefox. So convert is a really powerful program. And I see that grab is probably not responding, so let's force it to quit. So at any rate, what Dr. Planck is doing with his print convert is he's producing a program that can be run through that convert, and it will produce a really nice image, such as the ones you see right there. So that's what that function does, and then solve is the one you've already seen. Then notice that he has this time divided the methods between public and protected. So some of the methods are meant as helper functions that should never be callable by the user. So there's no reason for our helper functions to be public. So he made our checking functions, he made those be protected, and he made our recursive solver protected. And then he defined a vector to hold our 9x9 grid, and each line is 9 characters. So he's storing each line as a string of 9 characters. And then he's got this checker vector, which is going to always be 9 characters that he's going to use for checking his rows or his columns. Okay, and I'll explain why he does that in a minute. So he begins, and you can pretty much read that stuff in main. What we care about is the checking of things. So is row valid? So to check if a row is valid, he's checking to see if that number is valid. So he starts by setting all his entries in his checker to be 0. Then he goes through the grid for that particular row, and if it's got a number in it, he checks to see if that number has already been used. And if it has, then he returns false because the row can't be valid. If it is, then he sets the grid, or I'm sorry, he sets checker to be 1. Okay? So basically, he has already filled his number in at that point. And then he's checking to make sure that the row doesn't have any duplicate numbers. Now, he could have put his checker array here. Yet he chose not to. He made it an instance variable. Okay? This is kind of unusual to do that because really there's no need for the checker vector to stay there once the function has returned, right? So the question is, why did he put his checker vector in as an instance variable as opposed to just allowing it to be a local variable? I mean, clearly it works properly this way. So why would he make it an instance variable? Okay, it's a programming trick. It's done for efficiency reasons. By declaring it as an instance variable, that checker vector never disappears. And that means that it's only initialized once when the Sudoku object is created. Whereas if he declares it as a local variable, it is recreated every single time he calls is row valid or is column valid or is panel valid. So he's just trying to save some time here because he knows that he's going to be continuously using a 9-integer vector, and he doesn't want to keep allocating and deallocating it. So he's just doing a programming trick here for efficiency. I would not expect you, if you were implementing this solver, to know that trick. But I'm explaining to you why he did it. Okay? So it's just a trick to make the code a little more efficient. Okay. So the code for column is almost identical. You can look at it, figure it out for yourself. For panel, it's a little trickier because we're checking a 3x3 panel. So it could be any of the 9 panels. There's 9 panels actually in a Sudoku puzzle. So what he gives you is the starting row. The starting row could be 0, 2, or 5. And the starting column could be 0, 2, or 5. Do we agree with that? So those mark out one of the 9 panels. So that's what this is, starting row, starting column. And he's simply now, again, first setting his checker vector to be all zeros. Then he is going through his row. And notice he's only looking at 3 columns. Okay? And then he looks at, he's going through 3 rows. This outer one is going through 3 rows. So I should have, let me erase this. He's actually going through 3 rows. And then the inner loop is going through 3 columns. And then what he's doing is for each entry in the panel, he's checking if it's not equal to an empty. He is saying if that number has already been seen, it's not valid. Otherwise, we set that particular entry in checker to 1. If we get all the way through both loops without finding any duplicate numbers, we return 1 to indicate that the panel is valid. Okay, so it's a fairly simple checking procedure, no recursion or anything. Okay, and we already went through the recursive solve. I am not going to go through his print converter, but you can see it does all kinds of nifty things. It can set the size of a box, the gravity so that it centers the label, and some other gravity. So there's all kinds of commands that you can give to convert. You can actually find it online if you're interested. So if you Google convert image converter, Unix utility. This one's not so easy to find, but here it is. It's done by Image Magic. And you can find out all the different options. And you can see there are plenty of options that you can give the convert program. So at any rate, it's a cool way that you can use to create images. In this case, he is creating a JPEG image. But it's beyond the scope of this course. So I'm not going to hold you responsible for what's in it, but if you're curious, feel free to look at the code. Okay. I would hold you responsible, because you certainly have had to do it, for being able to print stuff into a screen. And one thing I do want to point out about his code is that a lot of you get into a really bad habit when you're printing things. We say print the items in a row, separated by one space. And what you will do is you'll say something like for I equals 0, say I less than 9, I plus plus, and you'll say printf, say %d, and a space, say a sub I. What do you think is the issue with this print statement? Certainly print stuff, 23, then there's a space, which is a blank, 24, then there's a blank, 30, then there's a blank, 50. But what happens at the very end? There's a blank at the end. That's wrong typically. Okay, and a lot of you get in the habit of doing that. And I know that on some of the scripts, especially early in the semester, things don't work because you put extra blanks at the end of your lines. So you have to have some way of ensuring that you don't have blank spaces at the end of your lines. One way to do that is to say if I not equals 0, printf a space, and then you do your printf. So what happens is that you're printing spaces in front of rather than behind. So here, you're printing a space in front of every entry, except you don't print a space in front of the first one. Okay, so that's a common technique. This is not equal. That's a common technique for suppressing a space so that you don't end up with too many of them. That is what Dr. Planck is doing in his code right here. So he's printing his grids, and you'll notice down here that he's putting separators, but you don't want any kind of extra leading space in front of the first entry. And so what he's doing is he's saying if j is not equal to 0, print the extra space. So that's what that line is doing, is it is suppressing an additional space if that's the first entry in the panel. Okay, so in each panel, he doesn't want the extra space right there. Okay, he only wants the extra space right there or right there. So that's what this special thing right here is suppressing the extra space in front of each panel. Okay, everything else should be pretty self-explanatory if you look at that code. Okay, so questions about our Sudoku solver. Okay, in that case, it's on to look at trees. And this is one place where you might as well not look at the book, because the book has, in my opinion, a pretty confusing way of presenting trees. I would just look at Dr. Planck's notes and at the terminology that was presented in Wikipedia. So here's a basic tree. I've already showed you one, but here's what's called an expression tree. So this one's called an expression tree because it is representing a mathematical expression. So this is division. So this is the root. The top node in a tree is called the root. Okay, so the root is the top node. Okay, every other node is a child. Okay, so this root node has 2 children. Okay, so these are often called child nodes, and that is their parent node. So in this case, the parent node for minus is the /. Okay. In fact, let's do this a little more. Most of you are probably more familiar with family trees, so let's do it this way instead. So let's say that we start with Jerry. Okay, I suppose we could start with Adam, but that might get me in trouble. Okay, so let's say Jerry had 2 offspring, Sue and Mary. And then let's say Mary had 3 children, Nancy, Eber, and Frank. And let's say Sue had a single child, Joe. And let's say Nancy has 2 children who are Jerry Jr. and Susan. Okay, so that's also a trait, probably one that's more familiar to you. So again, Jerry's the root, and you can see here the reason why we call it parent is because trees were developed from the notion of family trees. So Jerry, Sue is a child of Jerry, Sue's parent is Jerry. Okay. We call the nodes that have no children leaves. So a leaf node is a node that has no children. An interior or internal node, interior or internal node, has children, has 1 or more children. Okay, and it looks like a tree. It looks like an upside down tree, right? And the reason we call the top one the root is trees have a root system and they grow up from the root. Well, in this case, the trees grow down from the root. Okay, so it looks like an upside down tree. With trees are 2 important terms. One is called the height of a tree. The height equals the longest path from the root to any leaf. Okay, the longest path from the root to any leaf. So in that case, what is the height of this tree? It is 3. So we say that this is 1 segment, this is 2, 3. So you could count the longest path is the number of segments. So a path is the number of segments from the root to any leaf. So by path, it's a count. So count the number of So that's the height of the tree. And then the other important term is the depth of a node. So we talk about the height of a tree. We talk about the depth of the node, and that is the length of the path from the node to the root. Okay, so, and this should have said the length of the longest path. Okay, so given that definition, what is the depth of Mary? Someone said it. 1. And the depth of Nancy? 2. What is the depth of Jerry? 0. So that's our so-called base case. You can actually define depth recursively. So in fact, depth has a very nice recursive definition. Depth of the root is defined to be 0. The depth of any node equals 1 plus the depth of its parent. So it has actually a very nice recursive definition. The height doesn't quite. Actually, the height has a recursive definition too. So let's see if we can get that. Actually, I'll let you. So the height is the length of the longest path from the root to any leaf. Let's suppose for a moment, actually there's a special kind of tree that is called a binary tree. A binary tree is a tree that can have either 0 children, 1 children, or 2 children. So a binary tree is one that looks like, say, this. Example of a binary tree. So every known node has more than 2 children. So binary tree equals a tree where each node has at most 2 children. Okay, and then, yes?
I'm not sure if you ever said this explicitly. Each node can only ever have 1 parent, right?
Correct. That's a very good and important thing. So in a tree, let's see.
So that means we can only have 1 root ever.
Yes, that's right. So a very good and important thing is that, so let's go to the next page. In a tree, every child has exactly 1 parent. So there can only be 1 root in a tree, which is different than obviously certain trees. I mean, trees in the wild. But yeah, in a tree, every child has exactly 1 parent. Okay, the root is the only node that has no parent. Yes?
So when you're trying to figure out the height, how do you tell the difference between the first leaf, which may not be as far out as like the second?
So you basically just have to count every single path. You have to go. So I'm going to show you a recursive definition in a moment that kind of lets you calculate it too. Okay, so the next thing to note about a tree, let's go back to his diagram. In a tree, every node is actually the root of its own subtree. So we often talk about subtrees. So that is a subtree. So every node in a tree is actually the root of its own tree. A leaf even is the root of a tree, of which it is the only element. Okay. So those are the important terms that you need to know about trees. And just like I had a recursive definition for the depth, so I said the depth of a node equals 1 plus the depth of a node's parent. You can also get it for height the height of a node. So you can talk about also the height of a node. And that is equal to 1 plus the maximum of the height of any child. And the height of a leaf is equal to 0. So that's our base case. So that's how you could actually also calculate with a computer the height of a node. Right? Because I defined height to be the length of the maximum length path from the root to any leaf. So the length of the path from the root to any of its children is 1. And then you add to that 1 the maximum height of any child. So that's a nice recursive definition for height.
But a leaf is technically a node.
A leaf is technically a node, but we say that a leaf has 0 distance from itself. Just like up here, same thing. I said depth of a node, and then I said the base case is the depth of the root. So I'm just defining what the base cases are. So questions about any of that? Okay. So then, as Dr. Planck says, trees are really nice for things. Here, it's useful for representing this mathematical expression. So in the left subtree, right here, we have the expression 5a plus 10b. And in the right subtree, we have the expression 14a to the 4th minus 28b. Okay, in this subtree, we have the expression 28b. So each subtree is defining its own expression. Okay, you saw family trees. Those were nice. We're going to show you in a moment how to use trees for organizing data. But before we do that, there are 3 ways you can traverse a tree. Okay, so to traverse a tree, we want to visit each node in the tree. So we'd like to do it there's 3 recursive ways to do it starting at the root. Okay, and they are called pre-order, in order, and post-order. So these are all traversals. So I'll illustrate them first. So pre-order says that when you visit a node, you do a computation, whatever computation you need to do, you do it immediately. So let's say what we want to do is print every node in the tree. So if we're doing pre-order, it means that as soon as we visit the node, we print it. So in this case with pre-order, we would print the slash. Then we visit the left child first. So we go here, and because it's also pre-order, we immediately print it. And now, given what I've said, where do we go next? The times. Yep, this times. Then we go to the 5. Then we come back up to the times, go to this A. Okay, now we've exhausted this tree, so we come all the way up, and we visit this one, which becomes 6. This is 7th, 8th, and so on that we visit. So if we were to look at the order, it would be of printing, this times right here gets printed, then this 5 gets printed, then this A gets printed, then this times gets printed, and so on. Okay. Pre or in order is only defined for binary trees. So in order only defined for binary. subtrees. And in order says visit, and we'll do it with a visit left subtree, to print the node, 3, visit the right subtree. So in that case, it would print it in the order that would give this nice expression here. So if we did in order, we would start here, but we would defer printing. So we would first visit the left subtree going to plus. But again, we would defer printing and go to this subtree. Again, defer printing and go to here. At this point, it has no left or right subtree, so we print 5. Okay, now we return, and because we're at this step, we print the node. Now we visit the right subtree, and again, it's empty, so we print A. Okay, now we come back up to this node. And because we're at step 2, we print it. And now we visit the right subtree. And hopefully you see we're actually printing the tree just like it's printed here, except without parentheses, obviously. So that's in order. And then post order, is visit each of your subtrees in left to right order, and then print yourself. Okay, so in that case, I'll let you figure out. So take a moment, and actually I'll give you a smaller tree. Just pretend that you're doing to print, let's say that the tree, I'm going to make it simpler for you. Let's say that was the tree. This is the tree right here. Figure out what is the order of the symbols if it is post order. So just take about a minute. Figure out what order, I would write it down, is the order in which the symbols are printed. By the way, this is another great test question. Simple and easy to grade and test your knowledge. So if you're at plus, that is yourself. The symbol. Okay, so print the symbol. So we'll say print the symbol. That your node contains. Yes, Stone?
Is it the standard to always visit the left first?
Yes. Mm-hmm. You can do what's called reverse pre-order and reverse in order and reverse post order, and then you would reverse it. So if I explicitly said reverse post order than you would visit it right to left. Yes?
It's kind of a separate question, but on the Wikipedia page that links to in his notes, there's a definition called degree, which is the number of subtrees of a node.
Mm-hmm. That's the number of children it has. It would be so much easier if it just said that the degree of a node was the number of children it has.
Okay. So I was thinking, for a node doesn't it only have one subtree, namely the subtree where it's the root, but it's saying each subtree where one of its children is the root?
Yes.
Okay.
Well, as I said, so Dr. Planck had a comment that it seemed like the Wikipedia entry was designed to confuse. And that's one of them. Just the degree of a node is the number of children it has. Okay? Okay, so what do we think will be the very first symbol that gets printed using post order? It would be 5. Very good, because what happens is we visit plus, except that we first have to visit its subtrees. So we come down to here. But we first have to visit 5. Since 5 has no children, we print it. Now what's the second thing that we print? A. Then the times. Then we come back up to here and we descend. So we come down and next we print 10. Then we print B. Then the times. And finally we come back up to here and print the plus. So that's post order. Let's say we wanted to evaluate the expression in this tree. Which of the 3 traversals do we have to use to evaluate it? In order, okay? So let's try that. Actually, let's just do it on the small one. Okay? So you think we're going to use in order. So let's say A has the value give A is equal to 10 and B is equal to 30. So we're going to do in order evaluations. So we do start with plus and now we visit that one. And we first visit this and it returns 5 as its value. And A returns what is its value? 10. So what does, oh wait a minute, that didn't work because we're doing in order. So since we're doing in order, as soon as we come back with 5, we have to try to do our multiplication. Does that work? Do we know the value of the right subtree yet? Nope, we don't. You might try to claim it was A, but let's say that it was that. Then you sure as heck don't know the value of the right subtree yet, right? So it doesn't look like in-order traversal is going to work for evaluating it.
But it prints it out in the right order.
It printed it out in the right order. Well, actually, to print it out in the right order is in order, right? But now I want to evaluate it. That is, I want to evaluate the expression.
But why would that not evaluate properly?
Because you can't evaluate, so let's actually do this. Let's say you've gotten 5 times A and you know that the result is 50. Can you now evaluate the expression without knowing the right-hand side? You can't really, can you? So if all I give you is that, which is what in order gives you, you can't evaluate what's on the right-hand side. You can't really do the plus until you know, you can't really perform the plus operation until you know the value of that, and you have to know the value of both operands before you can do the operation.
So it's going to print out all the values first and then the operator in order to get the correct operation?
So it's not printing this time. So I'm changing the operation. So the first time the operation was to print it. So if you're just printing the symbols, then to get it in this pretty, in this, to get it to print like that, that's you would use in-order traversal. Now I'm changing the operation. Now I want you to literally evaluate the expression. So you want to perform whatever operation is at that node. Okay? Now what I'm saying is you can't evaluate a node until you know the values of its two operands. So in-order traversal doesn't work because in-order traversal only gives you the value of your left operand. So there's a different traversal you have to use. There's one of the traversal that will give you the value of all of your operands before you perform the evaluation. Post order. So with post order, you would visit each of your subtrees in left to right order. So by the time you came back, you would know the value of all your operands. So now I've replaced 2. Now I'm no longer printing. I would compute the value of the node. Using its operator. So I guess what I'm trying to show is the traversal you want to use depends on the computation you want to perform. So if the computation was a pretty printing of that tree, you would probably use an in-order traversal. But if the computation was to evaluate the expression, you'd need to use a post-order traversal. Does that make sense? So, okay. So there you go. So he gave the same kind of definition. He said it's the action. So when we're doing a traversal, we want to perform some action. So pre-order, you'd perform the action first, then you recursively visit your children in order. Post-order, you first visit all your children, then you perform the action. In order, you visit your left child, you perform your action, and then you revisit your right child. And in order works only with binary trees. Okay, so for our purposes, having gone over family trees and expression trees, that's actually not how we're going to use trees in this course. We're going to use trees as search trees. So what we want to do is take a collection of data and organize it so that we can efficiently search it. Ring a bell? We did that first with hashing, and then we did it with lists, and we've also done it with arrays and vectors, and now we're going to organize the data using trees. And we want to organize the data in a way that makes it efficient to search the data. And specifically, we want to do it in a way that keeps the data somehow in alphabetical order. Okay? So, the way we're going to do that, here is some binary search trees. And what they have is the property that all the nodes in your right subtree are greater than you, and all the nodes in your left subtree are less than you. So that's right here. If a node has a left child, then that's a little more complicated than I want. So I'll say it my way. So all children in your left subtree are less than you, or are less than your value, and all children in your right subtree are greater than your value. Now, we will modify that for duplicates. Right now, we're assuming everything is unique. So if you look at the 4 trees there, All of them satisfy that property. Okay, the first tree trivially satisfies it because it has only one node. The second tree has two children, and indeed Binky is less than Fred alphabetically and Luther is greater than Fred. Okay, the second tree also satisfies the property because Fred is greater than Binky and Luther is greater than Fred. And the last one also is more complicated, but also satisfies it because everything in Binky's right subtree is greater than Binky. Everything in Fred's right subtree is greater than Fred, and everything in Fred's subtree is less than it. And that's true all the way down. So this holds for every node in the search tree. Also notice that they're not unique. Okay? Each of these has the same three values, but there's two different trees. And I could have a third one with Luther as the root. So if Luther were the root, I could have Fred and Binky, or I could have Luther, Binky, Fred. Those are all valid and all different. Right? According to my definition, each of those is a valid binary search tree. So binary search trees aren't unique. They can be, for the same set of nodes, you can have many permutations of the same tree. Okay? So here's two examples of trees that are not binary search trees. Okay? The reason that this one isn't is because all three of those values are greater than Binky. So that's not a legitimate binary search tree. This one's not legit because it's not binary. Okay? Now, they have nice properties, which is if you perform a in-order traversal on a binary search tree, an in-order traversal, so an in-order traversal, I could get that right, an in-order traversal, of, and I'm going to abbreviate a binary search tree as BST, visits the nodes in alphabetical order. Based on the definition that I gave you, that should be fairly clear, right? Because if I'm at a node, I said all the nodes to my left are less than me in alphabetical order, right? Then I visit me, and then all the nodes in my right subtree are greater than me in alphabetical order. So I have visited all nodes less than me in alphabetical order, then I print it myself, and I visited all nodes greater than me. And this is true for every node, therefore I must have visited the nodes in alphabetical order. Okay, so a nice feature of binary search trees is you can traverse them, and you'll traverse them in alphabetical order. That's nice because they maintain the nodes in alphabetical order, something that hash tables don't. At least, now here's another nice thing. Let's say it's perfectly balanced, meaning that at every node there are as many nodes in your left subtree as in your right subtree. This one isn't balanced. Okay? But let's say you had one where it's Luther And then let's say we had Daisy, and we have Binky and Fred, and then we have, doesn't really matter, actually I don't want Luther, I want Luigi. I want Luigi. No, I don't want. Yeah, no. Shoot. Probably Luther wasn't the best choice. We'll choose some other names. Let's choose Nancy. And then we'll choose Mary.
Can a tree always be balanced with any number of nodes?
No. So the only time it's completely balanced is when it's called a complete tree like this, where every node at each level has a complete complement of children except at the leaf level. So in fact, the only perfectly balanced tree is one that is complete. Don't worry about those terms, but that's what one that has where every child at each level has a full complement of children except at the leaf, and the leaf none of them do. That's a complete tree and it's perfectly balanced. So what that means is that if there's n nodes, so if there are n nodes in a completely balanced tree, then the height of the tree is log n. Okay? And that is because each child subtree will have n divided by 2 nodes. And if you divide n by 2 log n times, you get 1. So a binary tree that's perfectly balanced means half the nodes will be in the left subtree and half the nodes will be in the right subtree. And in each of those subtrees, we'll have a quarter of the nodes. And then in the grandchildren, each of them will be an eighth, and then a 16th. So you end up with a height of log n.
There's 7. No, right?
There. Mm-hmm. So,
Height would be log 2 of 8, though.
no, it'd be log 2 of 7. There's 7 nodes in this tree.
So round
The height is 2, you round down.
So it's not actually.
But, yes, it's kind of really log n minus 1 rounded.
So
It's close enough. Okay.
is binary search the only one that goes alphabetically through?
So with binary search, the advantage is it, in some sense, the nodes are kind of in alphabetical order. So it makes searching it very easy. Because let's say you want to find Fred in that tree up there. Okay? You only have to search at each point. You can eliminate half the subtree or half the nodes. So you start and you compare Fred with Luther. So since Fred is less than Luther, which side of the tree must it be on? Left. So you'd go to the left child, and since Fred is greater than Daisy, it must be where? Which must be right. So you kind of, it's very easy to find a node in a binary search tree because it's kind of keeping it in alphabetical order. And since a perfectly balanced tree has only log n levels, log n levels, you'll find it in what's called log n time.
So what about the one that's above that?
It's not balanced. And that
Is it?
mean this
no,
one?
No, go
This one?
That one, because
It's not a binary search tree. So this one would totally kill your algorithm because, so in order for your algorithms to work, it has to be a binary search tree. It won't work properly if it's not. Then all bets are off. Now the problem can be that you don't always end up with a nicely balanced tree. This one right here is not very balanced. So today and on Tuesday, we're just going to be talking about the simplest kind of binary search trees. These are called unbalanced because the order in which values arrive can cause the tree to be unbalanced. Later, we'll talk about so-called balancing algorithms that will keep the tree balanced after every insertion. Okay, but for the time being, it is possible for the tree not to be balanced, in which case it's not so hot. Okay. So, do we kind of understand, though, the so-called, okay, so if we want to add a node to a binary search tree, so let's say we want it to add Nancy. So think about this for a moment. Suppose I want to add Nancy. Think about which node Nancy should become a child of if we want to maintain this as a binary search tree. So it's going to be, okay, just a second. So we have votes for Luigi. So, okay, Mac, I'll start with you. If it's a child of Luigi, should it be a left?
No, it's
Oh, it's not. Pardon?
Waluigi.
You're right. It should be, and should it be a left child or a right child?
Left.
Okay. So explain to me your reasoning. You're right. Explain to me your reasoning.
Because it has to go right of Binky, right,
Right.
of Fred, right
Mhm.
of Luther,
Mm-hmm.
and then it's less than Waluigi.
Very good. So it goes right there. So did everyone follow that? Nancy is greater than Binky, so we go to the right to Fred. Then Nancy is greater than Fred, so we go to the right to Luther. Nancy is greater than Luther, so we go to Waluigi. I don't know where he gets these names. And
Mario.
pardon?
Mario.
Oh, they are? Thank you. Are all of these, or are these just, is it just Luther, are all of these Mario characters?
Just Luigi and Waluigi.
Okay, just Luigi and Waluigi and Daisy? Okay. Binky isn't Binky Pac-Man?
Yeah.
Okay. So there we go. Okay, so then Nancy is less than Waluigi, so it ends up as a left subchild. Okay, let's say we wanted to insert cat. Where does cat end up? Left of Daisy, because cat is greater than Binky, less than Fred, and less than Daisy. So that's how we do insertions. Okay, pretty simple. And finding stuff is just as easy because you employ exactly the same algorithm. So if I wanted to find Luther, I go to the right, and hey, there's Luther. So pretty easy. And if I wanted to find Brad, which nodes do I investigate? Well, I investigate more. So I investigate Binky, then Fred, then Daisy, and now we realize I'm not in the tree. Because Daisy, where would I be? If I were in the tree, where would I be? Somewhere to the left of Daisy, but Daisy doesn't have a left child, therefore I'm not there. So this is the find algorithm, not the insert. Okay, so we got find and delete. Now, you can also see why insertion order makes a big difference. So if my insertion order is Binky, Fred, Luther, I get this tree. Correct? Because Binky becomes the root, Fred goes to the right of Binky, and Luther goes to the right of Fred. if my insertion order, so what insertion order, well, there's two inserts. If I say Fred, Binky, Luther, I get this tree, right? Because Binky or Fred was first, Binky goes to the left of Fred, Luther goes to the right of Fred. If my insertion order is Luther, Binky, Fred, can you draw that tree? Luther, then where's Binky go? To the left. Where does Fred go? To the right. So you can see that the order in which I present the names determines the binary search tree I end up with. So intuitively, what is a horrible order for me to insert names? That's just going to kill me. Alphabetical order is going to kill me. I'm going to end up with a linear list in effect. So the worst possible thing you can do to a binary search tree is give it the names in alphabetical order. So you hope that the names come in random order. It turns out that the best possible case is the names arrive in random order. If they arrive in random order, then mathematically speaking, the chances are high that the tree will be balanced. Okay? It's not guaranteed because even if they come in random order, it's possible for them to be sorted, right? The odds are against it, but it could happen. If I flip a coin 5 times, I can get 5 heads, right? It's not likely. It's random, but it's unlikely. Okay, the last one is deletion. So there's 3 cases for deletion. Okay, case 1, so deletion. Case 1, the easiest case is that it's a leaf node. So for example, Daisy. If it's a leaf node, you just remove it, right? Makes sense? So leaf node, just remove it. So that's easy. Case 2, it has 1 child. Okay, so let's say that we delete Binky. It has 1 child. Okay, that's pretty easy too. We just promote its 1 child. So in this case, by deleting Binky, we make Fred the new root of the tree. Okay, let's make it a little more complicated. Let's say that our tree was Binky, Fred, Joe, Frank. Nope. Get something between there. Giselle and Nancy. So if I delete Fred, based on what I just said, what happens to the tree? What did I say happens if it has 1 child? Joe gets promoted, so that's our new tree. So that's pretty easy. You just make the 1 remaining child, its new parent becomes its grandparent, right? Basically, whatever the child was, its new parent becomes its grandparent. Okay, so the hard case is where you have 2 children. And I'll go down to Dr. Planck's example for that. So just give me a couple minutes and we'll be done for today. Okay, so let's say this is our tree and we want to delete Fred. So Fred has 2 children. Okay, what we do is we find the largest value in the left subtree. Okay, which is what in this case? What's the largest value in the left subtree of Fred? Fiona. Okay? So the largest value is going to be promoted. And we know, because it's the largest value in the left subtree, every other value in the left subtree must be less than it, right? We also know that every value in the right subtree must be greater than it. So it's okay to promote it. Okay, the only problem is that Fiona may herself have children. Can Fiona have 2 children if she is the largest? No, why not? What if she had a right child, then that child must be greater than her. So by finding the largest value in the left subtree, this value can have at most one. This value cannot have a right child. So we've reduced it to a case where it can have either 1 child or no children. So what we're going to do is find the largest value to delete this node, or delete the node, okay, delete the node with the largest value in the left subtree, and then replace the deleted value with the value from the left subtree. So what that means is we delete the node associated with Fiona. Fiona replaces Fred. And because Fiona was deleted, Ernie becomes the right child of Daisy. Make sense? Questions? Don't. Oh, go ahead. Mac.
Replacing the value that you originally wanted to delete with the value that you just deleted.
Bingo, exactly. First thing we'll do next Tuesday is review this and have you do one of deletion. So I'll give you a tree on Tuesday and let you practice with deletion, okay? So we'll probably go through all 3 cases again on Tuesday, but I'll have trees for you to do.